But don't worry, we had to set it up, and now we got some theorems coming. So today I'm going to introduce what's called Reidemeister's theorem, which is a pretty powerful theorem. Okay, so remember we were left with some questions about the whole topic, which is last time, right? We were left with the question. We were left with questions like, I guess, how many knots are there? You might think there's a lot because there's a table at the back of your book and there's ones on the cover, but now we know that even the ones on the cover, right, might all be the same. So, and the ones in the table in the back of the book, presumably, someone went through a lot of trouble carefully drawing. Presumably they're all different, but we don't know that. So, and even if we knew that, you might wonder if the list was finite. Like, how many numbers are there? Like, how many numbers are there? Infinitely many, right? But, you know, if someone gave you a book of numbers that ended at, you know, 10 to the 100 or something, you might wonder if there are more numbers, but then you think about it and you realize there's more. With knots, it's not so obvious, right? Because each more complicated picture you make, you would have to check with all the other knots you constructed and found are different. And you have to check all of those to see if it's different from the ones you already discovered, right? So it's a very complicated process, all right? So another question would be, a simpler version of the question is this, the unknot, is the unknot, that's the only knot. Right? In particular, right? In particular is the one knot that we've kind of been drawing again and again, which has a name. So this is called the unknot. This is called the trefoil. Is the unknot equal to the same as the trefoil? Are they really the same knot? Just two different pictures. Seems unlikely if you've been playing with the extension cord, but who knows? Okay, so now we're going to talk about these Reidemeister moves, but before I start, so if you start reading 1.3, they mention a new term. So the reason is sort of, to be a little bit more precise, I mentioned that knots can be defined precisely. So these allowable moves to take one knot to another position, the allowable moves, that can be defined extremely precisely too. We're not going to in this course. I think you have a basic idea we've been talking about it, but the term is ambient isotopy. So the term is, this is the type of deformation allowed. So this is the type of deformation, rearrangement, etc., that we allow when showing two knots are the same. So we're just going to stick with kind of the intuition there. If you look in section 1.3, I'll make a little note that in section 1.3, they kind of show you something a little weird. They're like, what if you were trying to do this? You know, you can't do it with a real extension cord, but you know, it seems allowable. You know, and you might say, well, it's kind of a weird thing to try to do. Basically, it's this thing where he keeps shrinking this part of the knot to like a point. But, and at each stage, it's not intersecting itself, and you didn't tear the knot. So you might think, is that allowed? But if you think about it, most of you would never try something like that. So I think most of, you know, if you just stay with the naive idea, you're not going to accidentally do some sort of weird move that's not actually allowed by ambient isotopy. But the definition of kind of something like this is best left, I think, for an undergraduate, like upper level undergraduate, knot theory kind of course, or a grad gadget level kind of course, but you know, at that level you're more anal retentive about everything. Like if you ever take heavy duty like sort of calculus at a university, like they'll define everything extremely rigorous using set theoretic notation, like even what a number is and stuff like that. And you know, we don't need to, you know, you guys know how to use numbers without doing that, right? So that's what we're going to do with knots. So I'll just make a little comment. Beginning of 1.3 has an interesting example of what's not allowed. So something to think about, but no need to bust your head over it, of what is not allowed. Okay. So the reason we have to introduce the term, though, is later we're going to talk about other kinds of deformations that we do with the pictures on the plane. And so ambient here, right, if you talk about ambient sort of space, like even when I said space earlier in the first day, remember someone asked me, is space three-dimensional or are you talking about two-dimensional space? Which is kind of actually a kind of sophisticated question. I would assume most of you think space is three-dimensional. But in any case, if I talk about ambient space, you guys sort of think of the space in the room, right? Not the space on a sheet of paper or something. So we're going to define a term called planar isotopy. So ambient isotopy is what we've been doing with the knot in three-dimensional space. But we would like to do a similar kind of thing in the plane with our pictures. And the reason is we don't really care if our pictures are so exact, right? Like if we draw a trefoil like this and someone else draws a kind of cruddier picture, like they're really shaky, they've had a rough night or something, all right? And they draw something like that, you can kind of imagine if the blackboard was made out of rubber and I kind of went like that, it would kind of look like that. But notice the important thing is I'm not talking about like getting a different looking projection by moving the knot around and projecting it. I'm talking about just moving the sheet. Like you can imagine if your sheet of paper was more flexible or you got a lot of sweat on it because you have sweaty hands and it got distorted, it might kind of look like this, right? But essentially nothing really changed. There's still three crossings, three sort of intersections in the projection, and there's still three, and still stay the sort of same underlying configuration. It's just that it's not maybe perfect, like this is not exactly perfect either, but you don't have to be, that's the point. So let me just mention that planar isotopy similar kind of deformation, is similar, like compared to ambient isotopy. So similar kind of deformation to ambient isotopy, but not to a knot in 3 space, not to a knot, not to a knot, but in space. We use it in the plane containing a knot projection. So, we keep talking about these projections and doing stuff to projections instead, and you'll get a much better idea after today, much better idea. We're going to, to some degree, what we're going to learn after today is we can live in the world of pictures and doing just modifications to pictures and distorting pictures, in a two-dimensional way, and essentially all of knot theory is sort of contained in that. So we no longer